Okay, so my name is Adam. I'm from a company that's called Tamar. We do scale-up for startups. And I have very orange slides for you. A very set of orange slides. Anyway, so I'm here to tell you about a very good experience we had with a client of ours. They're called Vuser. And basically what we did, we just changed a single element in their stack from Seri to Storm. And we had a huge advantage. As you can see from the slide. Actually, so what they want us to do is to take their very nice product, which was mostly Pythonic, had some stateful parts, and was relatively small scale, and just make it work for basically every user in Tijuana. And Tijuana is not a small village. It's like something like 2 or 3 million people, and most of them have more than one cellular phone, and some cellular phones have more than one instance of the app. So it was a serious job for the backend. And basically what the app does is it's doing geo-matching. It takes active users and live questions, which can both move around the space, and it matches them according to some business logic. And that led us to think in critical sections, because that's the way Storm works. So we took those critical sections, those parts which are extremely heavy in compute, and we try to minimize their state dependency between each other. And not only that, we try to do it in a way that if we can eliminate state at all, it would be awesome, because that's the way we can achieve maximum scalability. So that took a really fresh take on geographic matching. Basically what we did was mostly use a whiteboard. Most of the work was done by just redesigning the entire system. And we found those critical sections. The first critical section is sample space reduction, which is a big way of saying, let's take just part of the entire world in order to do your calculation on. And that's a fairly common technique. It's just called soft decisions. And we did that using rtree, which is a Python class, in order to stay in the client's ecosystem. And well, rtree is behind the scenes. It's built with C, so we got good performance from it. So the second critical section was optimal matching. We took those soft decisions, those subsets of the entire data, and we applied our business logic, or the client's business logic, to this data. And we did this using Redis, and the code actually just runs inside of the Storm cluster, and it gave us very nice results. But the problem with it, the results was too nice, because we had some mismatch handling to do. And because the optimal matching algorithm worked so fast, we had concurrency problems. So basically when you have a message that cannot find a match, you have to dehydrate it, just to put it on the side for a while. And this while can vary from seconds to days, depends on the business logic. And that required for us to build our algorithm basically from scratch, and it's kind of fresh algorithm. So we had to do a lot of work on it, but we decided let's look at the logs first. And using our elk-based logs, we just saw that most of our use of this class is fairly basic, and so we can do just a basic input grouping algorithm. So we have those 3 sections, and now we want to put them together. So as I said before, we started using Storm. That's where we started from. So, and Storm, what you do, you have all these critical sections, and just okay, so this critical section connects to this critical section using this API, give or take, or this tuple. And we just did. You just take your Python code, because we use streamparse and not really Storm, and just shoved it all in. We wrote a very 40-line closure code just to build the topology. And by using streamparse, we kept using the client's ecosystem, which was Python. And that was the extreme value we got from only using one stack choice, using Storm, and specifically streamparse, which is the Python port of Storm. Thank you. You're welcome to look at our blog at nullterminalblog.com. So.